I kayaked once before.
All right, lesson 10.
Where's my pencil? I need a pencil. My breakfast was a Cliff Bar. A Cliff Bar and a cup of coffee. That was my breakfast. Oh, no, that's the way to start the day. Cheesecake?
Okay, so yesterday we started talking about series, and we saw that we can evaluate or we can find out if an expression has a limit as the variable approaches infinity. We saw some rules for determining that. So today we're going to talk about an infinite series. It may not be reasonable to add together the terms of an infinite series. An infinite series is one that continues on forever. However, there are situations where this occurs. And one of them is, you can see, you can express a repeating decimal as the sum of an infinite series. Point for repeating. So the first number after the decimal is a 4. That's 4 over 10. The second number after the decimal is also a 4. That's 4 over 100. And the third number after the decimal is also a 4 because it's the third number after the decimal. That's the same as 4 over 1,000 and etc. Okay, so you can write a repeating decimal as an infinite series. So consider this infinite sequence. 1/2 plus 1/4 plus 1/8 plus, and again, dot, 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 all the way to 1 over 2 to the n. Remember, n is the term number. When n is 1, you get a denominator of 2. When n is 2, that's the second term. The denominator is 2 squared, which is 4. When n is 3, that's the third term. And the denominator is 2 to the 3, which is 8, etc. Right? So, if we took the sum of the first term, that would just be a half. The sum of the first two terms would be adding a half and a quarter together, which is 3/4. The sum of the first three terms, you'd add the first three terms together. Again, you need a common denominator for that, but you would get 7/8, and so on. So there's some more sums that are given there as decimals. The sum of 4 terms is 0.9375. The sum of 10 terms is there, and the sum of 16 terms is approximately that value because it had to be rounded. But you can see that the more terms that are added, the partial sums approach a value of 1. So the limit as n approaches infinity of s sub n, s refers to the sum of that series, is 1. But not all infinite series do have a sum. If a sum exists, then again we use that word convergent. If no sum exists, we say that it is divergent. Recall that the sum of a finite geometric series is defined by that equation. And there's actually two different ones that could be used. Okay, just whether you use a as the first term or t sub 1 as the first term. So this was back in 20-1, you learned about these. So a is the first term or t sub 1. R is known as the common ratio. So when you have a geometric series, that's where each term is found by multiplying the preceding term by a constant, as opposed to an arithmetic series where you add the same constant to each term to go from one to the next. So you learned about those in 20-1. Right now we're talking about geometric series where there's what's known as a common ratio. Each term is multiplied by a constant to go from one term to the next. Okay, so that's what the common ratio R is, and n is the number of terms. For an infinite geometric series, you can find out what that sum is by taking a, the first term, and dividing by 1 minus r, the common ratio, or t sub 1, the first term, over 1 minus r. We're going to see that if the absolute value of r is less than 1, then that would mean that a sum does exist. That is a convergent geometric series. Now, another way of saying the absolute value is less than 1 is basically saying that r is between -1 and +1. You see, when the common ratio is a decimal between -1 and +1, that's when the series will approach a sum. But when the common ratio is greater than 1 or less than -1, then no sum will exist. Also, when the common ratio is 1, positive or negative, once again, no sum will exist. So, for each of these questions, before we find the sum, we need to find out if it exists or not by finding R, the common ratio. The common ratio must be between -1 and +1 for a sum to exist. And you can find the common ratio by taking any two terms, successive terms, and dividing the second one by the first. In each case, that'll give you R, the common ratio, if it exists. And that will be true for question number 1. You can find R, the common ratio, by dividing either the second term by the first term or the third term by the second term. Either way, you get the same value. R, the common ratio, is 1/8. Whether you divide the second term by the first or the third term by the second, it's the same answer. Remember, the common ratio is what you multiply each term by to go from one to the next. So if you work backwards and divide them, you get the common ratio. So because the common ratio is between -1 and +1, a sum will exist. And we can find out what that sum is by using that formula. And it's A over 1 minus the common ratio. A, the first term, is 8 over 1 minus 1/8. Right? Remember, R is the common ratio. So that'll be 8 or 8 over 1 divided by, on the bottom, I'd write this 1 with the denominator of 8. That would be 8 on 8. Take away 1 is 7 on 8. And to divide fractions, we multiply by the reciprocal. So we'd multiply by 8 over 7 and get 64 over 7. So there's your answer. The more terms that you add on to that series, the closer the sum will get to 64 over 7. That's what the sum will approach, 64 over 7. Remember, it's a limit, so it'll never actually get there. Okay? It'll never actually get there because it is a limit. All right, question 2. Again, the first step is to find out if there is a sum. And that sum will be found by using the formula, but first we have to make sure that R is between -1 and +1. And to find R, we'll divide the second term by the first term. We're going to divide 1/3 by 3 over 1, so that would be the same as 1/3 times 1/3, which is 1/9. So the sum will exist. And we can find out what that sum is by using the formula. And again, the formula is A, the first term, over 1 minus R, the common ratio. In this case, the first term is 3 over 1 minus 1/9. So it's 3 over 1 divided by 8 over 9, because the 1 would be 9 over 9 minus 1 over 9 is 8 over 9. And that'll be 3 over 1 times 9 over 8, which is 27 over 8. So there's that sum. So again, this is a limit. It is what the sum is approaching, not what it equals, but what it is approaching. The more terms you add on to that series, the closer the sum will get to be 27 over 8. Number 3, We start by finding r, the common ratio, by dividing the second term by the first term. So that'll be negative 1/4, which you would also get if you divide the third term by the second. 4 divided by negative 16 is still negative 1/4, or if you divided the fourth term by the first, negative 1 divided by 4, negative 1/4. So because r, the common ratio, is between negative 1 and positive 1, the sum will exist. And it'll be a, the first term, over 1 minus r. So you're subtracting r, and in this case, r is also negative. So we're going to have negative 1/4. The minus minus becomes a plus positive. So it'll be 64 over 1 divided by, and in this case, it's going to be 1 plus 1/4. 4/4 plus 1/4 is 5/4. And dividing by 5/4 is the same as multiplying by the reciprocal. So we'll multiply by 4 over 5, which will give us 256 over 5. So there's the value of that sum. Again, it's what the sum is approaching. Okay? For number 4, when you find the common ratio for this, by dividing the second term by the first, or the third by the second, or the fourth by the third, you get the same value every time. It's negative 1, so therefore this is divergent. No sum exists. A sum will only exist if the common ratio is between negative 1 and positive 1. So in this case here, we'll check the common ratio. If we go second term divided by the first, we can reduce that by dividing top and bottom by 4 and get negative 3/4. Let's just see if that is the same if we divide the third term by the second. You can divide top and bottom there by 3, and again you'll get negative 3/4. Okay. So because r, the common ratio, is between negative 1 and positive 1, there is a sum. The sum will exist. And it can be found by taking the first term over 1 minus the common ratio, which is negative 3/4. So it's 16 over 1 divided by, again, the minus minus becomes a plus positive. It'll be 4/4 plus 3/4, which is 7/4. Dividing by a fraction is the same as multiplying by the reciprocal. So that'll give us 64 over 7. So again, the more terms that are added onto that series, the closer the sum will get to be 64 over 7, but it'll never actually get there because it is a limit. Now with number 6, when you look at that, you should immediately see that something's not quite right, because the common ratio to go from the first term to the second term would be 1/5, but after that, the common ratio changes to 1/2. So what we would do in this case, we would just consider this part of the series to be an actual geometric series. Starting with the 1, there is the same common ratio to go to one term to the next. So we're going to have to find the sum using just that part of the series and then add the 5 on after. That's what we'll do. So again, you can see by inspection that r, the common ratio there, is 1/2. And so the sum for that part will be a, the first term, over 1 minus r, the common ratio, which is 1/2, This will be 1 over 1 divided by 1 minus a half is also a half. And dividing by a fraction is the same as multiplying by the reciprocal, so you can do it that way, or you can also say 1 divided by a half is 2. But then we have to add the 5 on after. And so there's your answer. In this case, the more terms that you add to this series, the closer the sum will get to be 7. But again, it'll never actually get there. So we started the lesson off talking about the fact that one application of an infinite geometric series is expressing a repeating decimal. Okay, and so we can use this to write a repeating decimal as a rational number in the form a over b. So in this case here, this number 2.37 could be written as 2 plus. The first 0.37 would be 37 over 100. There's 2 decimals there, the 3 and the 7, so you have to divide by 100. The next 37 would be 37 over. Now we had 2 zeros on the previous number. This time we have to have 4 zeros. 37 over 10,000. Every time you add another multiple 37, the denominator will increase by 2 zeros. There's 2 digits in the 37, so the denominator will increase by 2 more zeros. And that will continue on forever. So again, this is similar to the last example we looked at, because the geometric series actually doesn't start until the first 37 over 100. That's the first term of the geometric series. That's where you have a common ratio of 1 over 100. If you multiply 37 over 100 by 1 over 100, you'll get 37 over 10,000. And then you keep multiplying by 1 over 100. So our sum will be found by taking the 2 at the start plus, and then we have to use our formula for an infinite geometric series, which is a, the first term, 37 over 100, divided by 1 minus r, which is 1 over 100. So this will be 2 plus 37 over 100. And when we simplify the denominator, this 1 would be written as 100 over 100 minus 1 over 100 will give us 99 over 100. Multiply by the reciprocal, and the 100s cancel, and we will get just 37 over 99. Okay, and so we can write this as obviously a mixed number, 2 and 37 over 99. We can write it as an improper fraction by going 99 times the 2, which is 198, plus 37, which gives us 235 over 99. So you may remember from previous math classes, whenever you had a repeating decimal, that if you have 2 digits repeating, it's always those 2 digits over 99. That is true. Okay? But now you see why. This is where it comes from. If there's 1 digit repeating, it's always that digit over 9. If there's 3 digits repeating, it'll be that digit over 999. That is true. But now we see why. Okay? So in this case here, looking at number 2, again, the repeating part doesn't start until you get to the 35. So this number could be expressed as 2.1 plus The first 35 would be 35 over 1,000 because the 5 is 3 decimal places or 3 digits after the decimal. So to get that number, which would be as a decimal 0.035, it's 35 over 1,000. But because there are 2 decimals that are repeating, each term will be 35 over 2 more zeros than the last one. So the last one had 3 zeros, the next one would have 5 zeros. It would be 100,000, and so on. So 2.1 will be 2 1/10 plus, now the rest of this will be a geometric series with the first term of 35 over 1,000, and that's divided by 1 minus r, the common ratio, which again is 1 over 100. Because there are 2 digits repeating, each denominator will have 2 more zeros than the previous one, and you get that by multiplying by 1 over 100. So 2 1/10 would be 21 over 10 plus, this will be 35 over 1,000 divided by, this one would be 100 over 100 minus 1 will be 99 over 100. So to divide by a fraction, again, we multiply by a reciprocal. So this will be 35 over 1,000 times 100 over 99. So you can divide top and bottom by 100, which will take 2 zeros off the bottom there. And this leaves us with 21 over 10 plus 35 over 990. And to add these together, we'll need a common denominator, which would be 990. So the 10 on the bottom would have to be multiplied by 99. Okay, just to confirm that, 10 times 99 will give us the 990. So the top is multiplied by 91 as well. 21 times 99 is 2,079. So now you can add those together. Plus 35 is 2114. And these are both divisible by 2 because the last digits are even. So 2114 divided by 2 is 1,057. 990 divided by 2 is 495. So it's 1,057 over 495. And you can check that, right? We need to get 2.135 repeating. So if we take this rational number that we just found, 1,057, and divide it by 495, you get the right repeating decimal. So you can check it. Okay? Okay, so that's it for this lesson.